21st of January 1968, North Star Bay, Thule Air Base, Greenland. A Strategic Air Command B-52G, call sign Hobo 28, carrying 4 B-28 thermonuclear weapons crashed onto the sea ice after an onboard fire forced abandonment. Within hours, joint United States-Danish teams marked a debris and contamination footprint roughly 1 mile wide by 3 miles long on the frozen bay. Early field notes reported plutonium, uranium, americium, and tritium in surface samples, and nasal swab screening began for exposed personnel. 9,837 swabs taken, 335 showing detectable alpha activity. The contamination has been relatively fixed in the ice and snow, a State Department brief assured, adding a gentleman's agreement to remove large volumes of contaminated ice and debris. But a July 1968 accounting would state, no parts of the 4th Secondary have been identified. That number, and what precisely it described, would shape the response, the clean-up logistics, and decades of public controversy about what remained under the ice. Artifact: Mission card for B-52G 58088, a clipboard document listing crew, fuel load, and 4 B-28FI weapons configured for strategic airborne alert. The mission card was routine: hard head flight, Thule monitor patrol, tail number 580188, 7 crewmen, 4 B-28FI thermonuclear weapons in the bomb bay, standard refueling orbit over Baffin Bay, then a slow racetrack loop west of Thule Air Base. The purpose was visibility. Strategic Air Command wanted eyes on the ballistic missile early warning system radar, a massive phased array face scanning the polar approaches for Soviet launches. If the Soviets ever struck, that radar would give the first warning. The patrol guaranteed a nuclear-armed bomber overhead, ready to respond, ready to verify that the radar still stood. It was the 21st of January, 1968. Cold sunlight angled low across the sea ice. The B-52G had been airborne more than 20 hours, tracing its assigned pattern. Inside the pressurized crew compartment, the navigator checked coordinates, the radar navigator monitored systems, the pilots watched fuel flow and engine parameters, everything nominal. The refueling boom had topped off the tanks hours earlier. The next orbit leg would bring them back over the ice cap toward the radar site. At approximately 1500 hours Eastern Standard Time, a heater malfunction in the lower crew compartment began to smoke. The fire spread quickly through insulation and wiring bundles. Circuit breakers tripped. The co-pilot reached for the fire suppression handle, but smoke thickened faster than procedure allowed. Within minutes, visibility in the cockpit dropped to arm's length. The pilot ordered bailout. 6 crewmen ejected successfully over the sea ice. The 7th, the navigator, did not survive the ejection sequence. The unmanned bomber, still under partial power, continued west-northwest. At 15:39 EST, it struck the frozen surface of North Star Bay, roughly 7.5 miles west of Thule Air Base, on sea ice covering salt water approximately 600 feet deep. The impact shattered the airframe. Fuel ignited. The 4 B-28FI weapons broke apart in the fire and wreckage. Strategic Air Command declared a broken arrow, the Pentagon code for an accident involving nuclear weapons. Within 2 hours, base security cordoned the crash zone. The first survey teams reached the site by 1800 hours, instruments clicking in the sub-zero wind. Alpha probes registered contamination on blackened ice. A radio teletype message reached the Pentagon, the Atomic Energy Commission, and the State Department by nightfall. Impact site shows surface contamination. 4 weapons involved. Debris field extensive. Danish authorities notified. The mission had been designed to guarantee readiness. The B-52 fleet flew continuous airborne alert, Operation Chrome Dome, to ensure that even a surprise Soviet strike on American bases could not destroy the entire bomber force on the ground. One leg of Chrome Dome looped over Greenland, maintaining a nuclear-armed presence near the BMEW's radar and the northern early warning perimeter. The plan assumed reliability, crew discipline, and controlled responses to any malfunction. The risk calculus considered flight safety, weather, and navigation, but not what would happen if a heat event failed over a politically sensitive non-nuclear zone. Denmark hosted Thule Air Base, under a 1951 agreement. The Danish government had long maintained a public stance against nuclear weapons on Danish soil. The exact status of Greenland, a Danish territory, remained diplomatically ambiguous. The United States had deployed nuclear-capable forces to Greenland before, and SAC bombers routinely overflew the island. But the official Danish position, reiterated in the Folketing, the Danish parliament, was clear: no nuclear weapons stored in Denmark or its territories. The airborne alert was technically an overflight, not storage. That distinction had sufficed until 1539 EST on the 21st of January. Major General Richard O. Hunziker, Chief of Disaster Control for SAC, arrived at Thule within 24 hours. A base camp took shape on the ice: tents, generators, fuel drums, survey instruments. The camp was named Camp Hunziker. A command post coordinated with the AEC, the Danish Radiation Safety Office, and the US State Department. By the 22nd of January, survey crews had walked the debris field under portable floodlights, flagging grid stakes every 50 meters. The zone stretched roughly 400 feet wide and 2,200 feet long, blackened by jet fuel and JP4 combustion residue. Snow samples bagged and tagged, nasal swabs distributed to every worker entering the perimeter. The patrol had been meant to protect the radar site. Instead, it created the greatest political test of the US-Danish nuclear understanding since the base agreement was signed. The mission card, with its neat typed entries, now anchored an international incident. And the real question was not what the bomber had been doing in the air, but what 4 broken weapons had left on the ice and under it. Artifact, alpha probe and fiddler scintillation detector, handheld instruments for surface contamination surveys, the first tools to quantify what the crash had scattered across the ice. The first readings came within hours. A health physicist from the Base Radiation Safety Office stepped onto the blackened ice with an alpha probe in one hand and a clipboard in the other. He swept the probe slowly across a patch of soot-darkened snow. The meter needle jumped. He noted the count rate, moved 3 paces west, swept again. Another spike. He marked the position with a numbered flag. By the 22nd of January 1968, survey teams had outlined the contamination footprint. The debris field centered on the impact crater, where shattered aluminum and steel lay scattered across the ice. Contamination spread downwind in an elongated plume, shaped by the prevailing northwest breeze during the fire. The longest axis ran roughly 1 mile by 3 miles. Surface samples registered plutonium-239 and plutonium-240, the fissile isotopes at the core of the B-28 weapons. Uranium-235 and uranium-238 appeared in debris and in fine particulates on the snow. Americium-241, a decay product of plutonium, showed up in alpha spectroscopy. Tritium, from the weapon's fusion components, marked scattered fragments. The instruments told a consistent story. The high explosives in each weapon had detonated or deflagrated on impact, fragmenting the uranium and plutonium cores and scattering actinides across the surface. No nuclear yield had occurred. The weapons required precise implosion sequences that an uncontrolled crash could not replicate, but the radiological inventory was now distributed across a frozen bay instead of contained inside bomb casings. The Atomic Energy Commission dispatched observers from the Division of Biology and Medicine. Danish radiation experts arrived from Copenhagen and from the Risø National Laboratory. SAC Disaster Control established a decontamination line at the perimeter. Boots scrubbed, outer clothing bagged, nasal swabs administered. Every person entering the controlled zone received a dosimeter and a respirator. Every person exiting surrendered the dosimeter for reading and submitted to a nasal swab. A small cotton swab inserted briefly into each nostril, then sealed in a numbered envelope and sent for alpha counting. By the 24th of January, 96 hours after impact, the tally stood at 9,837 nasal swabs administered. 335 showed detectable alpha activity, a measure of inhaled or deposited particulates. Urine samples followed. 756 workers provided bioassay specimens for longer-term intake assessment. The results indicated surface contamination transfer, dust on gloves, breath vapor in cold air, but early reports emphasized that airborne concentrations remained low. The contamination has been relatively fixed in the ice and snow, one cable summarized. The actinides were not volatilizing or dispersing widely. They were locked in frozen matrices, adhered to soot and debris. That fact shaped the next decision. If contamination remained fixed, it would stay in place until the spring thaw. When the sea ice melted, contaminated material would sink into North Star Bay, a shallow inlet with tidal exchange to Baffin Bay and the Arctic Ocean. The radiological inventory would dilute over time, but the immediate plume would enter the marine food chain. Local Inuit communities harvested seals, fish, and shellfish from these waters. The Danish government had a clear interest in preventing that outcome. On the 16th of February, 1968, a State Department cable recorded a gentleman's agreement. The United States would undertake to remove about 50% of the contaminated ice and snow. The phrase was carefully chosen. 50% represented a compromise between cost, logistics, and diplomatic reassurance. The actual contamination mass was unknown. Surveys were still mapping hotspots, but the number offered a baseline for planning. Within days, the baseline proved inadequate. New grid surveys extended the flagged perimeter. Instruments registered counts per minute in sectors previously assumed clean. Wind patterns during the fire had lofted fine particles beyond the initial cordon. Each additional survey pass added flags, added tonnage, added shipping requirements. The technology was straightforward: alpha probes for surface screening, fiddler, field instrument for the detection of low-energy radiation, for more sensitive gamma and low-energy X-ray work. The detectors themselves were simple scintillation devices, reliable in cold if the batteries held charge. The challenge was coverage, a 1 by 3 mile zone, surveyed on foot in sub-zero wind chill under 24-hour Arctic darkness in January. Teams worked in rotating shifts. Flags multiplied. The map grew denser. By late February, the 50% removal target was effectively abandoned. The mapped contamination exceeded early estimates. The spring thaw was projected for late April, roughly 8 weeks away. If the cleanup was to prevent contaminated ice from entering the bay, the operation had to scale up immediately. The gentleman's agreement became a footnote. The revised goal: remove all practical contaminated material before melt. The instruments had forced the decision. The alpha probe and the fiddler, sweeping across. Blackened snow had turned a diplomatic courtesy into an engineering imperative. The readings, counts per minute converted to becquerels per square meter, then cross-referenced against melt projections, dictated logistics: how many bulldozers, how many tanks, how many ships, how many months. The operation now had a name: Crested Ice, and the target was no longer 50%. The target was everything the instruments could find. Artifact: typed information memorandum, background on B-52 crash near Thule. A State Department brief summarizing the accident, the weapons involved, and the diplomatic stakes. The memorandum arrived on Secretary of State Dean Rusk's desk on the 22nd of January 1968, less than 24 hours after the crash. The subject line read, "Background on B-52 crash near Thule." The text was concise: 1 B-52G, 4 thermonuclear weapons, impact on sea ice, contamination detected, Danish authorities notified. The final paragraph outlined the political dimension. The Danish government has maintained a policy against nuclear weapons on Danish territory. Greenland's status under this policy has been ambiguous. This incident may require clarification. That understatement marked the beginning of a diplomatic effort that would shape not only the cleanup, but the future of United States nuclear operations in Greenland. Denmark's declared stance was clear and public: no nuclear weapons in Denmark or its territories. The position had been reiterated in the Folketing, affirmed by successive governments, and embedded in Danish political identity during the Cold War. Yet Thule Air Base, a United States installation on Danish-administered Greenland, was a cornerstone of North American air defense. The BMEW's radar scanned Soviet missile trajectories. SAC bombers refueled over Baffin Bay and orbited Greenland's west coast. The base agreement, signed in 1951, permitted American military operations, but did not explicitly address nuclear weapons. For 17 years, the arrangement had functioned through careful ambiguity. The United States did not volunteer details of weapons deployments. Denmark did not press for them. The airborne alert over Greenland was technically an overflight, a transient presence, not storage. Chrome Dome missions carried live weapons aloft but did not land them on Danish soil. The distinction allowed both governments to maintain their positions. The United States preserved operational flexibility. Denmark upheld its non-nuclear policy in public discourse. The crash shattered that balance. 4 weapons had been confirmed aboard. Contamination, unambiguously linked to nuclear materials, now lay on Greenland's ice. The Danish press carried the story within hours. The Folketing demanded answers. Foreign Minister Poul Hartling faced immediate parliamentary questions. Had the government known about nuclear overflights? Had permission been granted? What assurances had been provided? Ambassador Torben Rønne, Denmark's representative in Washington, delivered a formal inquiry to the State Department on the 23rd of January. The message was direct. Denmark requested full disclosure of the weapons involved, the contamination scope, the cleanup plan, and, most significantly, future policy on nuclear overflights and deployments in Greenland. The phrasing was diplomatic, but the pressure was unmistakable. The accident had given Denmark leverage it had never possessed before. The State Department's response, coordinated through the Bureau of European and Canadian Affairs, acknowledged the accident and pledged cooperation on cleanup and environmental monitoring. On the question of future operations, the language was more cautious. The United States valued the defense partnership. Thule Air Base was critical to mutual security. Any changes to operational procedures would be considered in consultation with Danish authorities. Behind that carefully drafted reply, however, the calculus was shifting. On the 27th of January, an internal state cable noted that Denmark was likely to demand an absolute ban on nuclear overflights and storage in Greenland. The cable assessed the diplomatic cost of refusing versus the operational cost of complying. Chrome Dome missions could be rerouted. Airborne alert could continue over international waters or Canadian airspace. The radar itself required no nuclear-armed overwatch. The mission had been a visible symbol of readiness, not a tactical necessity. By mid-February, the outlines of a deal emerged. The United States would remove contaminated material from the crash site, an expanded commitment beyond the initial 50% target. Denmark would receive regular environmental monitoring reports and participation in survey work. In return, Denmark would accept carefully worded assurances about future operations. No nuclear weapons would be stored on Greenland, and overflights would be subject to review. The exact meaning of review remained vague, but the practical effect was clear. The continuous airborne alert over Thule would end. The agreement was never formalized in a single treaty. Instead, it unfolded through cables, ministerial statements, and parallel policy adjustments. The State Department's records captured the sequence: a crash, a parliamentary uproar, a negotiation conducted in memos and talking points. By March, the Folketing had voted on a resolution demanding absolute guarantees. The United States did not concede the language of absolute guarantees, but it quietly ended Chrome Dome operations over Greenland. The last Thule Monitor patrol flew in late February 1968. The memorandum that had landed on Rusk's desk in January had predicted the problem. The diplomatic resolution, reached over 6 weeks of exchanges, redefined the security relationship. The crash had given Denmark the political capital to enforce its non-nuclear policy, and the United States had chosen to accommodate rather than confront. The cost was operational flexibility. The benefit was alliance cohesion and, perhaps, a reduced risk of another broken arrow over politically sensitive territory. The cleanup, meanwhile, proceeded under new constraints. Every shipment, every press release, every technical term had to be vetted for Danish sensitivities. The operations language reflected diplomacy as much as engineering. What was called a survey in public cables was tasked as a search in classified guidance. The distinction mattered. Diplomacy, it turned out, would shape not only what was moved from the ice, but what could be said about it. Artifact, site survey map with penciled grid coordinates and count-per-minute annotations, the document that translated instrument readings into logistics and tonnage. The map filled a plywood board mounted on the wall of Camp Hunziker. Grid lines divided the crash zone into 50-meter squares, each labelled with alphanumeric coordinates. Survey teams added dots in pencil, each dot a measurement location, each annotation a count rate or activity estimate. By late January, the board was dense with marks. By mid-February, additional sheets extended the grid west and south, tracking contamination beyond the initial perimeter. The pattern was clear. The highest readings clustered near the impact crater, where weapon debris and jet fuel had burned together. Plutonium-239 and plutonium-240 dominated the activity, long-lived alpha emitters that registered strongly on the probes. Uranium isotopes appeared throughout the plume, both from weapon components and from scattered fragments. Americium-241, a decay daughter of plutonium-241, added to the alpha signature. Tritium marked areas where fusion components had fragmented. Concentrations varied widely. In the burn zone, surface samples showed localized plutonium deposition approaching 380 milligrams per square meter, a dense hotspot where molten metal had pooled and frozen onto the ice. Downwind, activity dropped off but remained detectable across the full 3-mile plume length. Wind during the fire had lofted fine particles, creating a skewed distribution. The northwest breeze stretched contamination away from the base, paralleling the coastline. The surveys used 2 primary instruments. The Alpha probe, a handheld scintillation detector optimized for alpha particles, provided rapid screening. A technician would crouch, sweep the probe across a square meter of ice, log the count rate, and move to the next position. The Fiddler, field instrument for detection of low-energy radiation, offered better sensitivity for low-energy gamma rays and X-rays, useful for confirming isotopic ratios and detecting americium. Both instruments required frequent calibration checks, especially in cold. Battery life shortened in sub-zero temperatures. Wind chill fogged the detector's windows. Teams learned to shield instruments inside parkas between measurements, preserving function in minus 30 degrees Celsius wind chill. The data accumulated daily. Each evening, survey teams returned to Camp Hunziker and transcribed field notes onto the master map. The dots clustered into zones. High activity sectors were outlined in red pencil, medium activity zones in yellow, low but detectable areas in green. The colors translated directly into removal priorities. Red zones required immediate excavation and packaging. Yellow zones scheduled for secondary sweeps. Green zones monitored for melt risk. By the end of February, the map documented more than 1,500 individual survey points. Statistical analysis showed that roughly 93% of detectable surface contamination fell within the 1 by 3 mile primary footprint. The remaining 7%, scattered particles carried by wind or tracked by vehicles, lay outside the cordon but still required attention. Each outlier added to the removal scope. The map also revealed gaps. Sea ice is not uniform. Pressure ridges, refrozen leads, and snow drifts created terrain that survey teams could not easily access. Some sectors were flagged incomplete coverage. Others were marked resurvey after snowmelt. The spring thaw would expose surfaces buried under drifts, potentially revealing additional contamination. The cleanup timeline had to account for that uncertainty. The isotopic inventory was quantified in becquerels, a measure of radioactive decay events per second, but field notes often recorded counts per minute for simplicity. To provide context, background radiation on clean Arctic ice registered roughly 10 to 15 counts per minute. Hotspots in the burn zone exceeded 10,000 counts per minute, a ratio of more than 600 to 1. A single chest X-ray delivers approximately 0.1 millisieverts of dose. The dose rate from direct contact with a high-activity ice sample could reach tens of millisieverts per hour if exposure were prolonged. Workers avoided prolonged contact. Bulldozer operators cleared contaminated material in passes, minimizing time near hotspots. Decontamination protocols emphasized speed and shielding. Earth and ice provided effective barriers to alpha particles, which penetrate poorly but required careful handling to prevent inhalation or ingestion. The map dictated everything. Transport planners used it to estimate tonnage. Logistics officers counted the red zones and ordered tanks. Schedulers projected man-hours based on grid density. The cleanup, in effect, became a problem of coverage and throughput. Clear each grid square, verify clearance, move to the next. The penciled dots on plywood translated into hundreds of thousands of gallons of contaminated slurry, packed into steel tanks, loaded onto ships, and sent south to the United States. The survey board was not just a record, It was the operation's blueprint, artifact, steel cylindrical storage tank, stenciled contaminated material, Thule 1968, one of dozens that carried plutonium-bearing ice slurry across the Atlantic. The tanks lined up at the site known as the tank farm, a staging area near the Thule harbour. Each tank was a standard industrial cylinder, roughly 8 feet in diameter and 20 feet long, welded steel with bolted hatch covers. Stenciled markings identified contents, destination, and hazard class. By March 1968, the tank farm held more than 30 tanks, with additional units arriving weekly by cargo aircraft and sea lift. The workflow was simple in concept, complex in execution. Bulldozers pushed contaminated snow and ice into wooden collection boxes, crude plywood bins, 3 feet on a side, open-topped. Workers in protective clothing shoveled box contents into larger hoppers, where the frozen slurry was mixed with water to create a pumpable fluid. The mixture was transferred by hose into the steel tanks. Each tank held roughly 5,000 gallons. When full, the tank was sealed, marked, and moved by truck to the harbour staging area, awaiting shipment. The operation had a name, Crested Ice. It was chosen for its bureaucratic neutrality, no dramatic phrasing, no direct reference to nuclear weapons. The name appeared on shipping manifests, in logistics cables, and on the tanks themselves. Crested Ice became the administrative shorthand for 9 months of cold weather excavation, the largest Arctic radiological cleanup ever attempted to that date. The initial plan had contemplated on-site disposal. Engineers proposed burying the tanks in permafrost pits near the crash site, sealed and monitored indefinitely. The permafrost layer in northwest Greenland extends hundreds of meters deep. Burial would immobilize contamination for geologic timescales. The option was cost-effective, technically sound, and precedented. Other military installations had disposed of low-level waste by burial, but Denmark rejected it immediately. The Danish position was explicit. Contaminated material must be removed from Greenland entirely. No burial, no long-term storage. Export to the United States. The decision transformed the logistics. Burial required pits, gravel caps, and monitoring wells. Export required tanks, cargo capacity, port facilities, and receiving sites on the far side of the Atlantic. The tonnage estimates climbed. At 50% removal, perhaps 20 to 30 tanks. At 90% removal, the goal now implicit in the revised scope, more than 70 tanks, possibly more. Each tank weighed multiple tons when full. Moving them from the ice to the harbour required tracked vehicles. Loading them onto ships required cranes and ballast calculations. 2 United States facilities were designated as receiving sites. Contaminated liquid slurry, melted snow, ice, and suspended particulates would go to the Savannah River site in South Carolina, where AEC liquid waste processing infrastructure could handle actinide-bearing streams. Solid debris, weapon fragments, metal casings, partial assemblies would go to the Pantex plant in Texas, the primary facility for nuclear weapon assembly and disassembly. Both sites had security clearances, radiological handling procedures, and classified material accountability systems. Shipments began in late February and continued through September. The tanks moved south aboard U.S. Navy cargo vessels and contract freighters, routed through Halifax or directly to East Coast ports. Manifest listed the cargo as radiological waste from defense operations, a phrasing that satisfied customs requirements without specifying the origin. Each shipment was logged, tracked, and confirmed upon arrival. By the time the last tank left Thule in early autumn, the total stood at more than 550,000 gallons of contaminated liquid and slurry, the equivalent of roughly 110 fully loaded tanks. The 9-month campaign required multi-agency coordination. The Atomic Energy Commission provided technical oversight and receiving site preparation. Strategic Air Command managed on-site operations and security. The U.S. Navy handled sea lift. The Air Force provided cargo flights for equipment and personnel rotation. Danish liaison officers monitored progress and reviewed sampling data. At peak activity, Camp Hunziker housed more than 300 workers, equipment operators, health physicists, decontamination technicians, labourers, cooks, and administrative staff. The Arctic environment imposed its own constraints. Equipment froze. Hydraulic lines required heating, diesel fuel gelled in tanks. Operators worked in insulated suits, limiting dexterity and visibility. Windstorms shut down operations for days at a time. In April, the spring thaw began, complicating excavation. Meltwater pooled in low spots, creating slurry without mechanical mixing. Pumps clogged with ice fragments. By May, the sea ice itself began to fracture, forcing crews to accelerate work in the outer grid zones before access routes broke apart. Despite the challenges, throughput remained high. Bulldozers cleared sectors ahead of schedule. Tank-filling operations ran double shifts during periods of stable weather. Shipping coordination improved as port handlers learned the procedures. By June, the visible debris field had been reduced to a graded expanse of scraped ice, flagged with survey markers where final verification sweeps were pending. The cost was never fully disclosed. Unclassified summaries referenced significant expenditure and multi-million-dollar operation, but precise figures remained buried in classified budget line items. Estimates, pieced together from later retrospectives, suggested costs in the range of tens of millions of $1968, a substantial sum driven by the Arctic logistics premium, the extended timeline, and the transatlantic shipping burden. Crested Ice succeeded in its primary objective. It removed the bulk of measurable contamination from the crash site before the summer melt could disperse it into North Star Bay. Environmental surveys conducted in subsequent years showed residual activity at low levels, consistent with the 7% remainder outside the main cleanup footprint. The tanks, meanwhile, became artifacts in their own right, steel cylinders that had carried Greenland's snow and plutonium south, part of the physical record of what happens when strategic policy, diplomatic necessity, and environmental risk converge on a frozen bay at the edge of the Arctic. Artifact, Weapons Component Inventory Ledger, partial entry for secondary number 4, a single blank line that defined the controversy for decades. The ledger was a technical accounting document, not a narrative. It listed 4 B-28FI thermonuclear weapons by serial number, then itemized recovered components. Primary stages, the fission triggers. Secondary stages, the fusion assemblies. High explosive casings, tritium reservoirs, firing sets, and ancillary hardware. Each line corresponded to a physical object tagged by grid location, excavation date, and shipping container. Most lines had entries. One line did not. By July 1968, the accounting was complete enough for summary. Weapon debris had been sorted at Thule and shipped to Pantex, where specialists in nuclear disassembly examined each fragment. Uranium cylinders, sometimes called spark plugs in weapons design vernacular, though the official term was simply secondary component, were identified by metallurgical signature. Plutonium cores were inventoried by mass balance, cross-checked against known production records. Approximately 85% of the total uranium mass from the 4 weapons was recovered. Approximately 94% by weight of 3 secondaries, the fusion assemblies, was accounted for. The 4th secondary was not. The phrase appeared in an internal AEC report dated July 1968. No parts of the 4th secondary have been identified. The sentence was factual and precise. It did not claim the 4th secondary was intact, lost, or missing in the colloquial sense. It stated that no recovered debris had been positively matched to that specific assembly. The distinction mattered technically, but the public and political interpretation would blur the line. The weapons had broken apart violently. High explosives in the B-28 design surrounded the primary stages. On impact, the HE detonated or deflagrated, fragmenting the fissile cores and scattering plutonium and uranium across the ice. The secondary assemblies, cylindrical fusion stages fueled by lithium deuteride and containing uranium components, were physically separate from the primaries and more robust, but they too shattered under the force of impact and fire. Fragments were collected, sorted, and analyzed. Some pieces were large enough for unambiguous identification, others were not. The specific component of concern was a uranium cylinder within the secondary, what some weapons designers informally called a Marshall's baton, due to its shape, though the term never appeared in official documents. This cylinder contained uranium-235 and uranium-238 in a particular geometric configuration optimized for fusion boosting. Its presence or absence mattered because uranium-235 is weapons-grade fissile material accountable under AEC security protocols. Losing accountability, even in an accident, triggered procedural alarms. The July 1968 report triggered immediate internal review. Had the component been consumed in the fire? Unlikely. Uranium has a high melting point and would not vaporize. Had it been buried in ice or wreckage? Possible, but the survey grid had been thorough. Had it sunk through the sea ice into North Star Bay? Also possible. The impact had occurred on ice approximately 1 meter thick over water roughly 200 meters deep. Fragments could have penetrated the ice during the crash or melted through during the subsequent fuel fire. If the component had sunk, it would lie on the seabed beneath the impact point. That possibility defined the next phase, an underwater search. The operation was never publicly called a search, in deference to Danish sensitivities about lost nuclear weapons. Official statements use the term survey of the bottom under the impact point, emphasizing environmental monitoring rather than component recovery. Classified cables, however, were explicit. Locate the missing uranium cylinder. The phrasing in the ledger, no parts identified, was carefully chosen. It avoided the word lost, which implied negligence. It avoided missing, which suggested active concealment. It avoided intact, which might imply a recoverable bomb. The component in question was part of a secondary assembly, not a complete weapon. Even if found, it would not constitute a functional nuclear device, but it was classified material and its location was unknown. The accounting also had a statistical dimension. 85% uranium recovery meant that 15%, several kilograms, depending on the total load, remained unaccounted for. That mass could be distributed as fine particles across the plume, as fragments outside the surveyed grid, or as larger pieces on the seabed. The 94% figure for 3 secondaries suggested relatively complete recovery for those assemblies. The 0% figure for the 4th secondary stood out starkly in comparison. The political consequence was predictable. Danish officials reviewed the summary and focused on the gap. The Folketing demanded clarification. Was a nuclear weapon missing? The United States response was technically accurate but politically insufficient. No complete weapon is missing. A component from one weapon has not been recovered. The distinction satisfied neither press nor parliament. The narrative simplified to "lost bomb," a phrase that would persist in media coverage despite repeated official corrections. The ledger, meanwhile, remained a classified document for decades. Later archival releases, including a 2009 report by the Danish Institute for International Studies, provided context. The target of the underwater effort was a uranium-bearing component, what the report termed a Marshall's baton, not an intact thermonuclear device. The clarification came 41 years after the crash. For most of that interval, the phrase, "no parts of the 4th secondary have been identified," functioned as a proxy for uncertainty, fueling speculation about what lay under the ice and how thoroughly the site had been cleared. The ledger was not a mystery. It was a mass balance, a standard tool in nuclear material accounting. But mass balances have consequences. They determine what gets shipped, what gets searched for, and what gets explained. In July 1968, a single blank line in that ledger turned a cleanup operation into a diplomatic flashpoint and set the stage for an underwater search that would test the limits of technology, coverage, and political ambiguity. Artifact: underwater search dive plan with unsearched sector annotations, a map that showed not only what was surveyed but what was not. The dive plan covered the table in the operations tent. Concentric arcs radiated from a marked impact point, each arc representing a planned search sweep. Divers would descend through a cut in the sea ice, follow a weighted line to the seabed at approximately 200 meters depth, then traverse the arc pattern using sonar and visual inspection. The plan divided the seabed into sectors, each assigned a priority based on debris trajectories calculated from the crash dynamics. The operation began in April 1968, as soon as water temperatures and ice conditions permitted. United States Navy divers, augmented by specialized civilian contractors, established a dive station on the ice directly above the estimated impact zone. A heated shelter protected equipment and personnel. Air compressors, decompression chambers, and communication gear lined the perimeter. The ice itself was still thick enough to support the installation, but the seasonal melt was underway. The operational window was narrow, perhaps 4 months before autumn storms and refreeze made work impossible. The search was officially described as a survey of the bottom under the impact point, a phrasing designed to emphasize environmental assessment rather than weapons recovery. Internal tasking documents told a different story. A classified cable from AEC headquarters to the Thule site commander, later declassified with redactions, specified the objective: locate the uranium component from the 4th secondary. The cable used the phrase spark plug, weapons designer shorthand for the cylindrical uranium piece, and noted that recovery was desired but not operationally required. The priority was confirmation: establish whether the component was on the seabed, and if so, document its condition and location. The underwater environment imposed severe constraints. Visibility was poor, silt, organic matter, and low-light limited sightlines to a few meters even with artificial illumination. Water temperature hovered near freezing, reducing diver endurance and equipment reliability. The seabed was not flat, it sloped irregularly, with depressions and rocky outcrops that complicated systematic sweeping. Sonar provided some coverage, but distinguishing a metallic cylinder from natural rock or other debris required close visual inspection. By June, divers had completed roughly 60% of the planned search grid. They recovered additional weapon fragments, pieces of casing, small metal fittings, debris consistent with aircraft wreckage, but no intact secondary component. The search pattern prioritized the sectors directly beneath the impact point and immediately downslope, where gravitational settling would most likely have deposited heavy objects. Outer sectors, further from the epicenter, were scheduled for later sweeps if time permitted. Time did not permit. In July, ice dynamics shifted. The sea ice, already thinning, began to fracture and drift under tidal forces and summer warming. The dive station became unstable. By early August, cracks opened within meters of the shelter. Equipment was withdrawn. The operational commander ordered suspension of dive operations until the following spring. The suspension became permanent. Seasonal conditions, budget constraints, and shifting priorities ended the underwater effort before the full search grid was completed. The dive plan remained as a record, a map with checked sectors and blank sectors. Post-operation analysis noted that approximately 40% of the originally defined search area had not been surveyed. The unsearched zones included outer arcs and sections where seabed topography made systematic coverage impractical. Later reviews, including a 2009 Danish Institute for International Studies report, emphasized the coverage gaps. The search had been partial, not exhaustive. The distinction mattered for interpreting the results. Absence of evidence is not evidence of absence. The official conclusion, recorded in a September 1968 closeout memo, was carefully worded: underwater survey operations did not locate the component in question within the searched area. The phrase acknowledged both the effort and its limits. It did not claim the component was absent from the seabed, only that it had not been found in the sectors that were surveyed. The distinction was technical and precise, but public interpretation again collapsed the nuance. Press coverage referred to a lost bomb and failed. Recovery, language that overstated both the threat and the failure. The search had been constrained by season, equipment, and environment. Navy divers, working in near-freezing water with limited visibility, had swept more than half the target zone under difficult conditions. They had documented what they found and mapped what they could not reach. The operation was professional and thorough within its operational limits, but those limits left questions unresolved. Declassified cables from the period reveal the internal tension. One message from the site commander to SAC headquarters noted that complete coverage is not feasible given ice movement and schedule. Another, from AEC observers, recommended that the search be considered complete for operational purposes, with recognition that gaps remain. The phrasing reflected pragmatism. Further effort would yield diminishing returns, and the primary cleanup, the removal of surface contamination, had succeeded. The underwater component, if present, posed no immediate radiological hazard. Uranium corrosion in cold seawater proceeds slowly, and any release would dilute into a large marine volume. The dive plan, with its checked and unchecked arcs, became the lasting artifact of the underwater effort. It documented the limits of what technology and time could achieve in 1968 under Arctic conditions. The plan showed honesty in its annotations: searched, unsearched, incomplete coverage. Those annotations, more than any summary statement, captured the reality. The operation had ended, but the search had not finished. Artifact: nasal swab envelope, numbered and dated, stamped Alpha Detected, one of 335 that documented internal contamination risk. The envelopes were small, manila, each containing a single cotton swab and a handwritten identifier. Worker number, date, time, and location within the controlled zone. 9,837 swabs were collected between January and September 1968 from personnel entering and exiting the crash site perimeter. Each swab was analyzed for alpha activity using scintillation counting. 335 envelopes came back positive, detectable alpha counts above background. The positive swabs indicated nasal contamination, plutonium or americium particles deposited in the nasal passages, either by inhalation or by hand-to-face transfer. A positive swab did not automatically mean significant internal dose. The nose is a filter, and particles trapped there often do not reach the lungs, but it flagged potential exposure and triggered follow-up bioassay, urine samples for longer-term excretion analysis. 756 workers provided urine specimens. The results varied. Most showed no detectable activity. Some showed low-level excretion consistent with minor intake. A small number showed elevated levels requiring medical follow-up and documentation. The immediate health physics response emphasized control and documentation. Workers with positive swabs were resurveyed, showered, and checked for residual contamination. Protective equipment protocols were reviewed and tightened. Better fitting respirators, double gloving, more frequent clothing changes. The nasal swab program continued throughout the operation, providing a rough real-time indicator of contamination control effectiveness. The long-term health question was more complex. Plutonium-239 is an alpha emitter with a half-life of 24,000 years. Once deposited in tissue, it remains biologically active for decades. Uranium isotopes have lower specific activity but similar long-term retention. The dose from internal contamination accumulates slowly over years, making acute effects unlikely, but raising questions about cancer risk over a lifetime. In the early 1990s, Danish researchers undertook a cohort study. They cross-linked the Thule cleanup rosters with Denmark's national health registries, comprehensive databases that track hospital admissions, cancer diagnoses, and mortality for all Danish residents. The cohort included approximately 4,322 workers, Danes, Greenlanders, and Americans, who had worked at the site and could be identified in registries. The study compared observed cancer incidence and mortality rates against expected rates for similar populations. The results, published in peer-reviewed journals, were cautious. The cohort showed elevated mortality from certain causes, including some cancers. The findings were statistically significant but difficult to interpret. Confounders were numerous. The workers were not a random sample of the population. They were predominantly male, younger than average, and employed in physically demanding Arctic labor, a demographic with baseline health differences. The unhealthy worker effect, a well-documented phenomenon in occupational epidemiology, complicates such studies. Workers willing to take difficult, temporary jobs in extreme environments often have different baseline health profiles than the general population. Smoking rates, alcohol use, and pre-existing conditions were not fully captured in the registry data. Moreover, the study lacked individual dose reconstruction. The nasal swabs and urine assays provided qualitative evidence of exposure, but did not yield precise dose estimates in millisieverts or REM for each worker. Without individual doses, the epidemiologists could not perform dose-response analysis, the gold standard for establishing causation in radiation health studies. The cohort could be compared to population averages, but the link between cleanup participation and specific health outcomes remained associative, not causal. Later follow-up studies, extending into the 2000s, continued to track the cohort. Some analyses reported persistent signals for specific cancer types. Others found no statistically robust excess. Meta-reviews noted the challenges: small cohort size, limiting statistical power, incomplete exposure data, long latency periods for radiation-induced cancers, and the difficulty of separating occupational exposure from lifestyle and environmental factors. The nasal swab envelopes, stored in archives, represented the most direct evidence of intake. 335 positive results out of 9,837 tests, a positivity rate of roughly 3.4%, indicated that contamination control, while generally effective, was not perfect. Workers had been exposed. The question was magnitude and consequence. Official statements from the period emphasized that no serious contamination had been encountered, a phrasing that reflected the absence of acute radiation sickness or immediately life-threatening doses. That was true, but the absence of acute effects did not preclude long-term risk. The cohort studies suggested caution without proving harm. The data pointed toward elevated risk signals, but the evidence stopped short of definitive attribution. The envelope stamped "Alpha Detected" became a symbol of that ambiguity. It documented exposure. It triggered protocols. It contributed to a dataset that decades later would inform public health research. But it could not, by itself, answer the question that mattered most to the workers. What was my dose? And what does it mean for my health? The answer required data that the operation, focused on logistics and throughput, had not fully captured. The cleanup had succeeded in moving contamination off the ice. The task of reconstructing individual exposure remained incomplete. Artifact, AEC briefing sheet, material balance summary, Thule incident, 3 percentages that reduced uncertainty and amplified controversy. The briefing sheet was 1 page, typed, dated July 1968. It summarized the results of 6 months of sorting, analysis, and accounting at Pantex and Savannah River. The numbers were precise. 85% of uranium mass recovered, 94% by weight of 3 secondaries accounted for, no parts of the 4th secondary identified. Beneath those figures, a note explained the methodology: metallurgical analysis, isotopic fingerprinting, cross-reference to production records. The percentages represented forensic certainty within the limits of post-impact fragmentation. The briefing was intended for internal use: AEC leadership, DoD liaisons, White House staff. It provided the factual basis for public statements and diplomatic communications. The key finding was reassuring in one sense. The majority of weapons material had been recovered and returned to secure custody. Nothing approaching an intact weapon remained at large. The dispersed contamination on the ice had been addressed by crested ice. The risk to the environment and public was minimal, but the numbers also sharpened the controversy. 85% recovery meant 15% unaccounted, several kilograms of uranium, distributed as fragments, particles, or possibly a larger piece on the seabed. The 94% figure for 3 secondaries implied near-complete recovery for those assemblies, making the 0% figure for the 4th secondary stand out starkly. The contrast suggested a discrete object rather than dispersed fragments, an interpretation that fed the narrative of a missing component. The briefing did not speculate on location. It noted that the seabed search was ongoing, the dive operations were still active in July, and that coverage was incomplete. It acknowledged the possibility that the 4th secondary's parts had been consumed in the fire, buried under ice beyond the survey grid, or scattered as unidentifiable fragments. The document avoided definitive conclusions where evidence was absent. The numbers were delivered to Secretary of State Dean Rusk and Secretary of Defense Robert McNamara. Both understood the political dimension. Denmark had demanded transparency and assurance. The percentages provided transparency, a quantitative answer to what happened to the weapons, but they also provided ammunition for critics. 15% uranium missing, 1 secondary unaccounted for. Those figures would dominate parliamentary debates and press coverage, overshadowing the 85 and 94% that had been recovered. In Copenhagen, The Folketing received a summarized version of the briefing through diplomatic channels. The Danish government issued a public statement acknowledging the cleanup progress and noting that the majority of weapon material has been recovered. The statement did not cite specific percentages, a deliberate choice to avoid focusing attention on the gap, but the press obtained the figures through leaks or unofficial channels. Headlines emphasized the missing fraction: 15% of uranium unaccounted for, fourth bomb component still missing. The phrase, "no parts of the fourth secondary have been identified," became a fixture of reporting. It was quoted in newspapers, repeated in parliamentary questions, and cited in later historical analyses. The phrasing was accurate, no identified parts, but its interpretation was elastic. To some, it meant a large, intact piece lost on the seabed. To others, it meant fragments too small or corroded to match forensic signatures. The briefing sheet did not resolve the ambiguity, it documented it. The percentages also became a point of comparison. In previous Broken Arrow incidents, recovery rates had varied, but the accounting had generally been less precise. Pre-digital records, less rigorous forensic methods. The Thule numbers represented a high standard of accountability. The fact that they stopped short of 100% reflected honesty, not failure. But honesty in technical accounting does not always translate to political reassurance. The briefing sheet, a single page of data, encapsulated the operation's success and its limits. It quantified what had been found and what had not. It provided the evidence base for closure. The cleanup was complete, the risk mitigated. But it also ensured that the July 1968 numbers would define public memory of the incident for decades. A small missing percentage, it turned out, could drive a very large political question. Artifact. Cold weather personal protective equipment, PPE checklist, annotated with field notes, a document showing the gap between design assumptions and operational reality. The checklist was standard issue: respirator, outer coveralls, inner layer, gloves, boot covers, dosimeter, alpha probe. Handwritten annotations crowded the margins: masks fog at 20C, glove dexterity poor, double layer, batteries fail, carry spares, decon water freezes in hose. The annotations told the story of procedures adapted under stress. Strategic Air Command radiological response doctrine had been developed for controlled environments: hangars, storage bunkers, processing plants. The protocols assumed heated spaces, reliable power, and stable equipment performance. Thule tested those assumptions. Minus 30 degrees Celsius wind chill, 24-hour darkness in January, equipment exposed to blowing snow and ice. Procedures had to adapt or fail. Respirators were essential. Plutonium and americium particles, if inhaled, posed the primary internal hazard. But respirator masks fogged when warm exhaled air met cold facepieces. Visibility dropped. Workers learned to breathe shallowly, to pause work and clear the mask, to rotate shifts more frequently to limit cold-induced respiratory stress. Some masks cracked in extreme cold. Elastomeric seals stiffened and leaked. Replacements were flown in, and fit testing was repeated. Gloves presented a trade-off. Thin gloves allowed dexterity for manipulating instruments, shoveling, and handling hoses, but provided minimal thermal protection. Thick insulated gloves kept hands warm but made fine motor tasks nearly impossible. Workers adopted a layered approach: thin inner gloves for contamination control, heavy outer mittens for warmth. Mittens removed briefly for tasks requiring precision. The result was slower throughput and increased risk of contamination transfer if inner gloves tore. Instruments drifted in the cold. Alpha probes relied on scintillation crystals and photomultiplier tubes. Both were temperature sensitive. Count rates shifted as electronics cooled. Calibration checks were performed every few hours using standard sources, but field conditions introduced variability. Fiedler detectors performed better. Solid-state components were more robust, but battery life dropped sharply. Technicians carried battery packs inside their parkas, swapping them into instruments as needed. Decontamination lines faced their own challenges. The standard procedure called for washing, with water and detergent, but water froze in hoses and spray nozzles. Heated decon tents were erected, but moving from the cold site to the warm tent created condensation, which then froze on equipment and clothing. The decon process became a stop-and-go operation. Scrub, rinse with heated water, wipe down, air dry in the cold to prevent refreeze. Throughput was slow. Workers spent as much time in decon as in the hot zone. The nasal swab program, designed as a rapid screening tool, worked well in principle but required careful execution. Swabs had to be collected immediately after a worker exited the controlled zone, before contamination could be transferred or lost through normal nasal clearance. The swabbing station was a small, heated tent at the perimeter. Workers lined up, removed respirators, and submitted to the procedure. A quick swipe of each nostril, swab sealed in an envelope labelled and logged. The process added minutes to every exit, but it was non-negotiable. The swab data drove decisions about re-entry, PPE adjustments, and medical follow-up. Dosimeters, film badges, and pocket ionization chambers provided cumulative dose records, but they measured external exposure, gamma and beta radiation, rather than internal contamination from alpha emitters. The badges were useful for tracking field time and verifying that workers were not approaching regulatory dose limits, but they could not assess inhaled plutonium. That required bioassay. Urine samples analyzed for alpha activity days or weeks after exposure. The delay between exposure and assessment was a procedural gap. Decisions had to be made on limited real-time data. The operation succeeded despite these constraints. Crested Ice removed more than 550,000 gallons of contaminated material over 9 months. Thousands of grid squares were surveyed, cleared, and verified. No worker developed acute radiation sickness. Nasal swab and urine data were collected and archived, but the procedural logs, annotated with cold weather workarounds, revealed a truth. The cleanup excelled in logistics metrics, tonnage, throughput, schedule, while dosimetric precision remained limited. The environment constrained what could be measured, and measurement uncertainty would complicate health assessments decades later. The checklist, with its field notes in the margins, documented a response that worked well enough, but not perfectly. Artifact, declassified State Department cable, excise sections marked deletion. A document showing what was said and what was withheld in the name of alliance management. The cable was dated February 1968, classified confidential, distribution limited to State EUR, Bureau of European and Canadian Affairs, DoD, and AEC liaison. The subject line read, Danish reaction to Thule incident, talking points. The body outlined guidance for US officials responding to Danish inquiries. Emphasize cooperation, stress, environmental cleanup, avoid specifics on weapon configuration, refer to underwater work as survey rather than search. Midway through the second paragraph, a block of text was marked deletion, information excised before declassification. The cable's existence and the deletions within it captured the tension at the heart of the Thule response. The United States and Denmark were allies, bound by NATO commitments and the strategic importance of Thule Air Base. Transparency served alliance cohesion, but transparency about nuclear weapons, their design, their vulnerabilities, their precise status after an accident, collided with classification protocols and operational security. The result was a calibrated disclosure, enough information to satisfy diplomatic obligations, not so much as to compromise secrets. The Danish government faced its own pressures. The Folketing, responding to public concern and political opposition, demanded answers. What exactly had crashed? What exactly was missing? The government had to balance those demands against the practical need to maintain the US defense relationship. The solution was a series of briefings, parliamentary statements, and joint communiques that provided facts without undermining security or political stability. The phrasing mattered. When asked about the underwater effort, US officials described it as a survey of the bottom under the impact point, a term that suggested environmental monitoring. Classified tasking documents used different language: locate the spark plug, recover the secondary component. The euphemism survey allowed Denmark to present the effort to Parliament as a precautionary environmental check rather than a weapons recovery operation. The distinction preserved political room for both governments. The phrase Thulegate emerged in the Danish press in the 1970s, a nod to the Watergate scandal and the implication of hidden truths. Journalists and opposition politicians pressed for fuller disclosure. How much contamination remained? What component was still missing? Had the search been exhaustive? The government released summaries but withheld details, citing security agreements with the United States. The result was a slow burn of suspicion and incomplete answers. Declassification came in waves. The US State Department released tranches of Foreign Relations of the United States, FRS documents, covering the 1960s, including extensive Thule material in the late 1990s. The cables revealed the diplomatic choreography, the early panic, the negotiation of cleanup terms, the crafting of public statements. But gaps remained. Key technical documents stayed classified. The exact design details of the BT-8 weapon, the forensic results from Pantex, and the precise target of the seabed search were not included. In 2009, the Danish Institute for International Studies, DIIS, published a comprehensive report. There is no bomb. They were not looking for a bomb. The report synthesized declassified US and Danish archives, interviewed participants, and clarified the central controversy. The underwater search, the report concluded, had sought a specific uranium-bearing component of a secondary assembly, what weapons designers informally termed a marshal's baton due to its cylindrical shape. The component was not an intact nuclear weapon, not capable of detonation on its own, and not a lost bomb in the popular sense. The search had been incomplete, the report noted, but the target was a piece of classified hardware, not a strategic threat. The DIIS findings aligned with technical realities. A thermonuclear weapon secondary is a fusion stage, fueled by lithium deuteride and incorporating uranium for fission boosting. The uranium component, enriched to weapons grade, is accountable under nuclear security protocols, but does not constitute a deliverable weapon. The distinction is critical for specialists, less so for public discourse. The phrase "lost bomb" had always been media shorthand, not technical description, but it shaped perception and policy debate for 4 decades. The report did not fully resolve the controversy. Questions remained. Why had the search been discontinued? Could the component still be found with modern technology? What long-term radiological risk did it pose on the seabed? The DIS authors noted that the uranium, if present, would corrode slowly in seawater, posing minimal environmental hazard. Uranium is less radiotoxic than plutonium, and cold Arctic water slows corrosion. Any release would dilute into a large marine volume. The radiological consequence was negligible compared to the political consequence. The declassified cables and the DIS report together provided the archival closure that the July 1968 numbers had not. They confirmed what had been sought, why it had not been found, and why the search had ended. They clarified that no parts of the 4th secondary identified referred to a component, not a weapon. They documented the diplomatic compromises that had shaped public language, and they showed, with deleted passages and euphemistic phrasing, the limits of what could be said even decades later. The cable with its deletion marks became a symbol of the gap between transparency and security. It showed that the Thule response had been honest within constraints, but the constraints were real. Allies could be trusted with facts, but not with secrets. The public could be informed, but not fully briefed. The cleanup could be documented, but not the full weapon design. The result was a historical record that answered many questions while leaving others marked deletion. The brackets, as much as the text, told the story. What happened at Thule was known, but what Thule revealed about nuclear operations remained, in part, classified. Artifact. Final Load Manifest, September 1968, stamped Crested Ice, complete, the administrative closure of the largest Arctic nuclear cleanup to that date. The last tank was lifted by crane onto the deck of a contract freighter in early September 1968. The manifest listed the cargo: steel cylindrical tank, contaminated material, origin Thule AB Greenland, destination Savannah River Site, South Carolina. The ship departed Thule Harbor on the 14th of September. A radiogram to AEC headquarters confirmed. Final shipment underway. Site demobilization in progress. The numbers told the operational story. more than 550,000 gallons of contaminated liquid and slurry had been removed. Ice, snow, meltwater, suspended particulates bearing plutonium, uranium, americium, and tritium. The material filled approximately 110 large steel tanks, shipped over 7 months aboard multiple vessels. Solid debris, weapon fragments, aircraft wreckage, contaminated equipment had been packed separately and sent to Pantex. The total mass of material removed from the site exceeded several thousand metric tons. Environmental surveys conducted during final demobilization showed residual surface contamination at low levels, consistent with survey detection limits, and the 7% remainder estimated to lie outside the primary cleanup footprint. The readings were elevated above natural background but below action levels for unrestricted use. Follow-on monitoring was recommended. The site was not declared clean in an absolute sense. It was declared clean to the maximum extent practical given operational constraints. The original target, articulated in February, remove 50% of contaminated ice, had been exceeded. The executed scope approached 93 to 95% removal of detectable surface contamination, a figure drawn from grid verification surveys conducted in August and September. The remaining 5 to 7% represented scattered particles, material in inaccessible terrain, pressure ridges, refrozen leads, and contamination below instrument detection thresholds. The cost, never publicly itemized, was reconstructed in later analyses. Estimates ranged from $30 to $50 million 1968 dollars, equivalent to several hundred million in 2025 currency. The expense reflected Arctic logistics, airlift, sea lift, cold weather equipment, extended personnel rotations, specialized waste processing at receiving sites. The operation had no precedent. Every procedure was developed on site or adapted from imperfect analogues. The timeline was 9 months, January to September, with peak activity from March through July. The work proceeded through Arctic winter darkness, spring thaw, and early autumn storms. Camp Hunsaker, at maximum capacity, housed more than 300 workers. Total personnel involved, including rotations, support staff, and technical advisors, likely exceeded 1,500 individuals over the course of the operation. The operational legacy was twofold. First, Crested Ice demonstrated that large-scale Arctic radiological response was feasible, given sufficient resources and time. The lessons learned, cold weather procedures, contamination control in extreme environments, logistics for bulk waste export, were documented and archived, informing future spill response and decommissioning plans. Second, the operation set a precedent. Political constraints, not just technical ones, determine cleanup scope. Denmark's insistence on export rather than burial transformed the response from a local engineering problem into a transatlantic logistics exercise. By October 1968, Camp Hunsaker was dismantled. The tents, generators, and survey equipment were airlifted out. The tank farm was empty. The debris field, scraped and graded, reverted to a wind-swept expanse of sea ice. Winter returned. Snow covered the site. Later environmental studies conducted by Danish and Greenlandic authorities in 2003, 2007, and 2011 found low-level residual contamination in sediment and biota, consistent with the long half-lives of plutonium and americium and the known limits of the cleanup. The final manifest, stamped and filed, closed the operational chapter, but the archival chapter remained open. The cleanup had ended. The accounting had ended. The questions about doses, about the seabed, about long-term environmental fate would persist. The tonnage ledger closed. The under-ice question did not. Artifact Dies Report 2009. Title page reading, "There is no bomb. They were not looking for a bomb." An archival conclusion 41 years late. The report was published in April 2009 by the Danish Institute for International Studies. It ran to more than 200 pages, synthesizing declassified US and Danish government documents, technical analyses, and interviews with surviving participants. The central finding was stated plainly on the cover. The underwater search had sought a specific uranium component from a weapon secondary, not an intact nuclear device. The The clarification was technical, precise, and decades overdue. The policy consequences of the Thule crash had unfolded quickly. Within weeks of the accident, Strategic Air Command ended continuous airborne alert operations over Greenland. The last Chrome Dome patrol carrying nuclear weapons over Danish territory flew in late February 1968. The operational rationale, maintaining a visible nuclear presence near the BMEW's radar, was judged not worth the political cost after the crash. Airborne alert continued elsewhere, over international waters and less politically sensitive regions, but Greenland was excluded. Denmark, for its part, formalised its non-nuclear stance. Parliamentary resolutions in 1968 and subsequent years demanded written assurances from the United States. No nuclear weapons stored in Greenland, no overflights without explicit notification. The exact phrasing of US commitments remained diplomatically ambiguous. Classified agreements, oral assurances, carefully worded public statements, but the practical effect was clear. Thule Air Base remained operational as a radar site and logistics hub, but its role as a nuclear staging area ended. The health legacy was more complicated. The worker cohort studies, initiated in the early 1990s, produced mixed signals. Some analyses showed elevated cancer incidence and mortality among cleanup participants. Others found no statistically significant excess when confounders were accounted for. The challenge was data quality. The nasal swabs and urine assays documented exposure but did not yield individual dose reconstructions in millisieverts. Without precise doses, epidemiologists could not establish dose-response relationships, the standard for attributing health effects to radiation exposure. A 2004 follow-up study, extending the cohort observation period, reported persistent mortality elevation in some subgroups, but noted that lifestyle factors, smoking, alcohol, occupational hazards unrelated to radiation, were incompletely captured in the data. The unhealthy worker effect remained a confounding variable. Later meta-analyses, reviewing multiple studies of nuclear worker cohorts worldwide, placed the Thule results in context. The signals were consistent with low-level occupational exposure, but not definitive proof of causation. For the workers themselves, the ambiguity was frustrating. Many had provided bioassay samples and undergone medical surveillance for decades. Some developed cancers, some did not. The question, did my participation in Crested Ice contribute to my illness, could not be answered with certainty for any individual. Compensation claims, filed in Denmark and the United States, produced inconsistent outcomes. Some workers received settlements, others were denied for lack of documented dose thresholds. The absence of precise exposure data, a consequence of the operational environment, and the limited instrumentation deployed, left the health legacy unresolved. The environmental legacy was more tractable. Danish and Greenlandic environmental agencies conducted periodic surveys of North Star Bay and the Thule region in 2003, 2007, 2011, and subsequent years. Sediment cores, water samples, and biota, seals, fish, mollusks, were analysed for plutonium, americium, and uranium. Low-level contamination was detected, consistent with the known cleanup limits. The activity concentrations were several orders of magnitude below levels that would pose health risks through consumption. The residual contamination, while measurable, did not constitute a public health hazard. The seabed question remained open. No further searches were conducted after 1968. Modern technology, remotely operated vehicles, synthetic aperture sonar, precision GPS, could theoretically complete the coverage that divers could not. But no government pursued it. The consensus, reflected in the DIS report and subsequent technical reviews, was that the unaccounted component, if present on the seabed, posed negligible radiological risk. Uranium corrosion in cold seawater proceeds at roughly 1 micrometer per year. A cylindrical component would require millennia to dissolve completely, and any released uranium would disperse into a vast marine volume. The environmental case for a new search was weak. The political case, satisfying public curiosity, achieving archival closure, was stronger but not sufficient to justify the expense. The archival record, expanded by successive declassifications, provided the clearest legacy. The FRU's volumes, the DIS report, the National Security Archive briefings, and the published epidemiologic studies together documented what happened, what was known, and what remained uncertain. The phrase, "no parts of the fourth secondary have been identified," written in July 1968, remained accurate in 2025. The component had not been found. The search had not been exhaustive. The uncertainty endured. But the record also fixed what could be known. The cleanup removed the bulk of surface contamination. The policy shift ended airborne alert over Greenland. The worker cohort was monitored, even if individual doses could not be reconstructed. The underwater search, incomplete, was documented. The archival releases clarified that the target was a component, not a bomb. The legacy was not closure, it was precision about the limits of closure. The title page of the DIS report, with its blunt capitalized declaration, captured the final archival verdict. There was no lost bomb. There had never been a lost bomb. There was a missing component, a gap in an inventory ledger, and 41 years of imprecise public language. The report could not recover what the divers had not found, but it could correct the record. And in the end, the record was all that remained. Measurements, manifests, cables, and a single unresolved line in a July 1968 accounting. The crash had been contained. The contamination had been removed. The policy had shifted. The workers had been tracked. The questions about doses, about the seabed, about individual health would persist as long as the isotopes themselves, decaying slowly in sediment and memory. 21st of January, 1968. B-52G serial number 580188, carrying 4 B-28 thermonuclear weapons, crashed onto the sea ice of North Star Bay, Thule Air Base, Greenland. High explosives detonated on impact, scattering plutonium, uranium, americium, and tritium across a debris field approximately 1 mile wide by 3 miles long. Immediate response. Joint United States-Danish teams cordoned the site. Within hours, 9,837 nasal swabs were collected. 335 showed detectable alpha activity. 756 urine bioassays followed. Cleanup, Operation Crested Ice, February to September 1968. More than 550,000 gallons of contaminated ice, snow and slurry were removed and shipped to Savannah River site and Pantex plant. 93 to 95% of detectable surface contamination was cleared. Cost estimated at $30 to $50 million 1968 dollars. Weapons accounting, approximately 85% of uranium mass, and 94% by weight of 3 weapon secondaries were recovered. July 1968, internal report stated, "No parts of the 4th secondary have been identified." Underwater search, April to August 1968. Navy divers surveyed approximately 60% of the planned seabed search grid before ice conditions forced suspension. The search was never resumed. Declassified documents later clarified the target, a uranium-bearing component of the secondary assembly, what weapons designers informally called a Marshall's baton, not an intact nuclear weapon. Policy consequences. Strategic Air Command ended continuous airborne alert operations over Greenland in February 1968. Denmark formalized its non-nuclear stance, receiving assurances on future overflights and storage. Thule Air Base continued as a radar and logistics facility, but its role in nuclear operations ended. Worker health, cohort studies initiated in the early 1990s, tracked approximately 4,322 cleanup participants through Danish national health registries. Some studies reported elevated mortality and cancer incidents. Others found no statistically robust excess after accounting for confounders. The absence of individual dose reconstruction prevented definitive attribution of health effects to radiation exposure. Danish and Greenlandic surveys in 2003, 2007, 2011, and beyond detected low-level residual contamination in sediment and biota, consistent with the known cleanup limits. Activity concentrations remained several orders of magnitude below health risk thresholds. The 2009 Danish Institute for International Studies report concluded, "There is no bomb. They were not looking for a bomb." The underwater search had sought a specific weapon component, not an intact device. The component's radiological risk on the seabed, if present, is negligible. Uranium corrosion in cold seawater proceeds slowly, and any release would disperse into a large marine volume. The phrase "no parts of the fourth secondary have been identified" remains accurate. The component was not found. The search was not exhaustive. The uncertainty endures. But the record fixes what can be known. The crash was contained. The contamination was removed. The policy shifted. The workers were tracked. The questions that remain are documented, not hidden. The legacy is precision about the limits of precision. If you value fact-based nuclear history, consider supporting this channel.